The next section is about thermal modeling with Laoss, and we showed two examples with PV and OLEDs. And I think there was a nice publication by, I think by Axel Fischer, who is in the audience here. He's an expert in modeling as well, and they also, in their publication, they have shown a nice measurement of Fraunhofer Comet OLED panel, a tabular panel, which is a rectangular panel, where they measured the heat temperature distribution as well as the luminance, and there was significant non-uniformities in the temperature. So at the boundaries here we see a lot of so this whitish area on the boundary, that's the hottest area, and on the luminance also where we have a lot of current, we have a lot of heat, but a lot of current drawn means also a lot of luminance. So the potential, probably the applied potential was, in the boundary region here we have almost the applied potential probably. That's why we have a lot of current. So that's just an example of a non-uniform OLED panel. I don't know much more about this. Maybe you can say something about it. It was it.
The potential comes from the outside and is very close at the conductivity close to what you apply, but then as you already explained, it will drop into the middle.
Yeah.
There was no metal grid.
No metal grid.
Drastic example of how shear resistance and thermal effects can then decrease the luminance in the middle.
Ah, yeah. So on purpose, a bad example on purpose, kind of, yeah. And I was told that if you take such a fresh OLED panel, it can happen that, they have this non-uniform behavior, but if the OLED starts to degrade there where we have a lot of luminance, then eventually you have a more uniform panel after several hours of operation. So this degradation can also help to get a more uniform OLED. But okay, there is this one example in Laos where electrothermal coupling is exemplified. It's called basic OLED thermal zip. So if you would go to your folder there where you can, it's called import from zip file on the upper left, you could open this example and let it run, or first investigate what are the input quantities. It's a bit, maybe was from zip. So if you go to after the geometry tab, go to device JVT of this example basic OLED thermal zip, and there you would you can see that the thermal coupling is activated. There's full electric thermal coupling, and that's the main choice. But then in the electrodes you also need to specify thermal sheet resistance, not only an electrical sheet resistance. So you need to specify two conductivities. And in the boundary conditions, in the thermal modeling, in the thermal modeling you also need to care how does the heat, can it escape vertically on the surface, on the top surface, on the bottom surface. There's a heat transfer coefficient describing how heat is transferring, or it may be a radiation law as well. So these are typical properties of thermal boundary conditions. There it is. I'm sorry it's not connected, but where you select the coupling laws, the first tab is electric coupling, the second electric thermal coupling. And then maybe I should still show it here. Yeah. So the first difference to the previous example is now we have full electric thermal coupling. And we have a JV, as before, we have a JV coupling law selected, but down here, that's the JV coupling law, again the same current voltage curve of an OLED, but now we can also select a refinement of the model. We could even adjust the coupling law according to the temperature. So instead of having a static current voltage curves, we can enhance the current at higher temperature, and that makes it more nonlinear. So what we do is we would have an original JV coupling law. I think it's this small f here, right? And then we modify it by this thermal activation formula. And the user can enter activation energy and the measurement temperature. And that will automatically adjust the current density for the new temperature that is found after solving for this, or when solving for this joule heating. And the thermal parameters are shown here. We have thermal conductivity in the stack. We have stack thickness, ambient temperature. That's relevant because the heat transfer always is with respect to the ambient temperature. We have a temperature on the electrode, and there is this heat transfer standard law. It's a linear law, so the temperature difference between electrode and ambient temperature drives the heat transfer away from the electrode, and the prefactor is this transfer coefficient, which is in this case 11 watts per square centimeter and Kelvin. And so we can choose two different heat transfer coefficients for the top and the bottom. It really depends what's the situation of the OLED panel, what's the surrounding. Is it air? Yeah. OLED efficiency.
This is how much is converted into light and how much is converted into thermal energy.
Okay. Okay, that's to considering that some power is transformed into light output, and so 20% is a typical light out coupling efficiency of an OLED. So here we can enter 20% as light power output, and 80% of the joule heating, 80% would be joule power. And luminance parameter, that's again as before. And okay, I think there was no sweep in this case. Oh no, there was a sweep, yeah. Was ist da gesweept worden? Was ist da gesweept worden? The applied voltage. Soll ich supporten? No. Okay. We have a variation, a sweep of the applied voltage and the resulting current. And then can we also look at the temperature? Well, we have for each applied potential, we can visualize not only the electrical potential, but also the temperature. Where's the temperature? Yeah. So this would be an example of the temperature. It's 356 Kelvin, quite strong increase of temperature at the edges, at the bottom left, bottom right edges of the OLED. That's also where we have most current being collected, most likely. That's the current. Yeah, indeed, from the current or from the potential distribution and the electric field, you would see where the current is flowing. So it is consistent with the resulting temperature. Okay. You have questions about this electrothermal model example? Yeah, yeah, yeah. It's the Joule heating term is current times voltage. Yeah, it's. I think it's we have it in the stack and in the electrode, right? Also, the electrode can generate heat.
Yes.
Yeah. No, it is. These two software are not yet coupled like this. You could simulate JV versus temperature with ZFOS and export it in ASCII file format and have several JV for different temperatures, and then Laoss would use it as a lookup table to select the right JV at the right temperature at position XY on the panel. So it would be physically correct simulation, but it's kind of two-step first, ZFOS and then in Laoss. Yeah. So at the moment you cannot sweep voltage in the big domain and do the fully coupled simulation between the two tools is not yet possible. Yeah. So far kind of standalone Laoss. Yeah. More questions about the software? I think this they're in the Laoss manual. You would also find some explanation about the Joule coupling term. Yeah. Okay. Then we can go back to the maybe presentation. Now there's another example of electrothermal PV module. Very small module because we only have two solar cells. So these horizontal looking, so this is a top view, one cell and the second cell, and they are interconnected like this schematic. That's now finally the schematic of the typical thin film interconnection, where one cell would extend further here. So this could be 1 centimeter width cell, and there's a small area where the top electrode is connected down to the bottom electrode of the neighboring cell. So the current would be collected in the stack here, flowing through this electrode, going down to the neighbor electrode, and then flowing back up to the neighboring cell. So this is a zigzag interconnection, very common in the PV industry for thin film solar cells. And we have modeled this in Laoss. So basically, you can imagine in Laoss, you just have to make sure that the original solar cell JV curve is describing the coupling between top and bottom electrode here. That's the solar cell. And here we have a conductivity, a very high conductivity between top and bottom electrode, to kind of short the two neighboring cells here. And then we see the electrical simulation as a potential distribution on the upper panel. And then we have a thermal simulation result. Some heat is generated here. You see the red area here indicates that's more, that's a higher temperature. And why do we have higher temperature there? The reason is that this sketch is a bit cut off. In reality, the solar cell is extended maybe 1 centimeter wide. So the current is being collected vertically and pulled to the left. And on this left side, on this left edge, we have all the current density concentrated. So along this line here, we have this higher temperature. That's the reason for the elevated temperature along this line, is because the current is collected on this edge here. The current comes from left and goes here. And that can even be seen if you make thermal imaging of a solar cell, you can actually see this elevation of temperature on this edge of the long solar cell. So it's not just a colorful picture, but can really be measured also with infrared imaging. And then the next solar cell, this dark blue area, this would be this edge over here. So the current comes from below and is collected on the left. So at this edge, we have a small current density, so only little Joule heating generated here, but more on the left-hand side. So again, there's a red edge here. And then the lower example is an assumption of some shunts. So here's a small dark spot, and the dark spot mimics an electrical shunt between the top and bottom electrode. And that means that a lot of current goes through that shunt. And in the end, we will observe an elevated temperature here. I think this green value, green-yellow, means, we have here 370 Kelvin at this spot here. And the surrounding is room temperature, but very locally we can have a very hot spot because the current flows through that electrical shunt. So this is an illustration of one can use Laoss to investigate solar cells with defects and how that affects the temperature distribution. And such kind of defects are also visible in thermal imaging of solar cells. And we have made a joint study with the Fraunhofer Institute in Freiburg. In Freiburg, they have fabricated an organic solar cell, just a single solar cell, which has a quadratic shape. And this quadratic solar cell had metal grid lines across. And now this image that you see on the left is a electroluminescence image, where the electroluminescence of the solar cell is emitted and detected by the infrared or by the camera. In this case, it's actually a visual camera, I think. And what we see here is that it's not obvious, but the way the solar cell is connected, we have a collection of current on the left-hand side, and so that's why we have more intensity in this image on the left-hand side. And we reproduce this situation in Laos. Matthias, who's sitting up there, did this work actually. You can ask him more questions how he did this. He actually tried to reproduce this measurement. So the measurement can be, can make a cross-section, and we see the measured blue lines here. That's the cross-section of the AL intensity, and the simulation are the dashed lines. And you see that because of the metal grid, there are these narrow dips where we don't have EL emission because it's a shadowing effect. But in the simulation, we have the metal grid, and even on the metal grid, we can also evaluate the current density. So in the simulation, we have a peak where we have a dip in the measurement. So that's a bit confusing. But beside that, you can notice that the agreement is very good. So for instance, the behavior, the distribution of light in between these metal grids, the valleys are well reproduced. The sharp valleys, ignore the sharp valleys because that's a measurement artifact, because you cannot access the EL light below the metal grid. But in the simulation we can, so that's why we have peaks in the simulation, but dips in the measurement. And overall, the task here was to reproduce the images for several different current densities from 10 milliamps per centimeter square to 100 milliamps per centimeter square. So that means that's the current we drive through the solar cell. It operates like an electroluminescent device. And we collect the current on the left-hand side, and there is an overall drop in this EL, or current, as we go to the right. And we were happy that we could reproduce it quite well, and the way which parameters needed to be adjusted. So there were some unknowns between the metal grids. There was P.PSS as a conductive electrode material with limited conductivity, And the exact value of this conductivity needed to be adjusted in the model in order to reproduce the measurement. That's how you can fit the measurement in the simulation, adjust some of the unknown or estimated values of conductivities, P.PSS. Yes, and another example we did, so we consider these validation examples. Now the next example is a mini module of four OPV cells, and here you see the typical interdigitated or series connected OPV cells where metal fingers were added for increasing conductivity. And in the lab we measured here the temperature rise in the module in a steady state IR measurement, so no lock-in technique, simple steady state heating measurement where the measured temperature profile is shown in red. So it's a cross section here in this line here, that's the red cross section, and the simulation shows the electrothermal Laoss simulation result shown in yellow here, and you see that we can reproduce the measured temperature profile with the Laoss temperature calculation here. Yeah, so the shape overall, yeah, is nicely reproduced, and in this other direction there is some variation. Here is a bit hotter than on the left, so that's more related to the fabrication uncertainties, that these OPV cells are not identical everywhere. But for us it was just nice to see that the overall shape could be reproduced by the simulation. Okay, now we have 10 minutes left, and so I'm happy to be more or less in time. Last topic is optics in Laoss. We have implemented or linked some ray tracing solver to the Laoss software. And one first demo example is a demonstration example where we have assumed a solar cell, which is down here. It's a quadratic high-efficiency solar cell, which is being illuminated by sunlight. But between the sunlight and the solar cell, we have a Fresnel lens, and the Fresnel lens has this typical shape, a circular structure. And what we want to simulate is we want to find out how much of the light illuminated in this incident area here is actually being concentrated on the solar cell. So the focusing effect is not ideal. You see that outside of this dashed area here, we still have some light hitting the detector plane. So in Laoss now we can move a detector plane to evaluate the light intensity. In vertical direction we can move the detection plane, and I think there was a light. You can evaluate the fraction of light that hits the solar cell, and this is an actual picture of some rays visualized. So we have collimated rays coming and then going through the lens and being focused on this in solar cell area here. That's the first example in the context of PV, and now a second example in the context of displays, OLED displays. We talked before about the electrical crosstalk, but also optical crosstalk can happen. This is an example of cross-section of an OLED display where we have red, green, blue pixels, but basically we have a white OLED covering all the pixels below here. It's this orange layer that represents the OLED, and between the pixels we have a PDL, a pixel definition layer. And now in this first demonstration example, we simplified the structure, and we just assumed, because we didn't know for sure what's the topography of the PDL, in the first step we just assumed everything is planar, but nevertheless we wanted to check how much light is escaping from this, for instance, from the green pixel here, how much light goes from the green pixel into the white pixel, and how this is built up. We have RGB color filters placed in front of the white OLED. So so what happens? So in the bottom we have the white OLEDs everywhere, and there is a top layer on the cover glass which contains color filters for green, red, and blue. And now if we turn on the green, I think the green one was turned on, and then we see that depending on the wavelength of light, we can check that some green light, this is now the blue light coming from the green pixel, meaning that there's a white OLED below which contains blue light, and this blue light can escape through the white color filter and also through the neighboring blue pixel where we have a blue color filter. So this is an unintentional light leakage in the neighboring pixels coming from this green pixel. And this is the kind of problem the display industry wants to solve by adjusting maybe or making sure that the geometry here of the pixel definition layer can be altered, or also the geometry of the color filters, how they are placed and what distance are they placed with respect to the bottom white OLED. So as an input for this kind of simulation, you have to get an angular spectrum of a white OLED. In this case, we just use a ZFOS simulation of emission spectrum versus viewing angle. That was input as a description of each of these 4 white pixels. They were all represented by this angular spectrum I have shown. And for the color filters, we also need to enter a transmission and reflection property of the color filter. And in the end, we get the map. I mean, one way to plot the result is in this intensity map. Another way is to visualize the angular dependence for a viewer that is placed far away from the display. And he will see a polar dependence, but also an azimuth dependence of light intensity. And you can see that there's not purely rotational symmetric, there can be some pattern in the far field as well. And finally, you can imagine that if we implement, now that we will soon release the optical module, and maybe we can also couple that to the other modules, the electrical and thermal modules. Afterwards, Roman will make a demo of the optical module, and now I'll conclude the presentation. I will conclude that we believe that this Laoss software is a useful tool for OLEDs and solar cell simulation and optimization. It allows to design modules and single cells and solar cells, also optimize power efficiency and tuning the electrode materials to get uniform emission in OLEDs. And you've seen that we have electrical, optical, and thermal modules of this software. Thank you for your attention, and now let's go have a demo. Thank you.